What's happening, my friends? Welcome back. We've got some natural lighting today. Before we get into the video, I've just started up the Daily Dance newsletter, free daily newsletter breaking down the latest in STEM every single day. Anyway, let's get into this video. 3 ways to destroy the universe. Let's do it.
One day the universe will die, but why and how? And
not sure we know that. Maybe,
will the universe be dead forever? And how do we know that?
Maybes on top of maybes.
First of all, the universe is expanding. And not only that, the rate of its expansion is accelerating. The reason? Dark energy. Dark energy is a strange phenomenon that scientists believe permeates the universe. Until 1998, we thought that the universe must...
If you're new here, we just watched Kurzgesagt's dark energy video.
...work a bit like a ball that you throw into the sky. The ball moves up, but at some point it has to come down again. But the expansion of the universe is actually speeding up. That's like throwing a ball up and watching it fly away faster and faster and faster. Where is this acceleration coming from? Well, we don't know, but we call it dark energy. Einstein thought of it first and then decided it was stupid. Now, astrophysicists have decided it is plausible. Trouble is, this is all very theoretical, and we don't actually know what the properties of dark energy are. But there are various theories, and they lead us to 3 scenarios for the end of the universe.
There's many more as well.
1. The Big Rip. Since its birth, the universe has been expanding. For unknown reasons, new space is created everywhere equally. The space between galaxies expands, so they move apart. The space inside galaxies also expands, but here gravity is strong enough to keep them together.
So this explanation of it might not actually be what's happening. You should go watch that dark energy one where we talk about it.
In the Big Rip scenario, the expansion accelerates up to a point where space expands so fast that gravity can't compensate for this effect anymore. The result is a Big Rip. At first, only large structures like galaxies are torn apart since space between the single objects expands very fast. Next, big bodies like black holes, stars, and planets die. Their gravity isn't strong enough to keep them together, so they dissolve into their components. In the end, space would expand faster than the speed of light. Atoms would now be affected, and they would just disband. Once space is expanding faster than light, no particle in the universe can interact with any other particle anymore. The universe would dissolve into countless lonely particles that won't be able to touch anything else in a strange, timeless universe. And you thought you felt lonely.
So the individual galaxies would actually have their dark matter, gas, and eventually stars ripped out of them from the outside in. So the outskirts of galaxies would basically be stripped away first, right? And then eventually even the cores of these galaxies would be stripped down. So yeah, right in those final moments, basically, protons, neutrons will be ripped apart into quarks and gluons, and just moments before the fabric of space and time itself is demolished by dark energy. So with current data, the very first step of this big rip would start happening at around 60 to 80 billion years from now, at minimum. But, once that first step occurs, tearing apart structures on scales of about approximately 20 million light years, everything else will happen pretty quickly. We're talking only hundreds of millions of years before all of the galaxies are torn out of their home groups and clusters, right? And then it's only tens of millions of years until stars are then ripped out of their galaxies. And then next, it's only a few months, right, until the outer planets are ripped away from their parent stars. And then weeks before those inner planets are then, doomed as well. And then a few minutes for our planet to be destroyed, and then fractions of a second for molecules and atoms. The greater the amount of force and energy that's required to tear something apart, basically the less time there is remaining until the universe itself comes to an end.
2. Heat death, or a big freeze. In a nutshell, the difference between the Big Rip and heat death is that in a heat death scenario, matter stays intact and is converted over an incredibly long but finite period of time into radiation while the universe expands forever. But how does this work? Let's talk about entropy. Every system tends towards the state of highest entropy, like when we have a latte macchiato. Initially, it has different regions, but over time they will cool down and disintegrate until it's uniform. And this also applies to the universe. So while the universe gets bigger and bigger, matter slowly decays and spreads out. At some point, after lots of generations of stars, all the gas clouds necessary to form stars will be exhausted, so the universe will turn dark. The remaining suns will die. Black holes will slowly degenerate and evaporate over trillions of years due to what's known as Hawking radiation. When this process is complete, only a dilute gas of photons and light particles remains until even this decays. All activity in the universe ceases at this point. Entropy is at its maximum, and the universe is dead forever. Unless, theoretically, it might be possible that after an incredibly long amount of time, there might be a spontaneous entropy decrease as a result of something called quantum tunneling, leading to a new Big Bang.
So the higher the entropy, the less energy there is for useful work in a system. And so if you couple that with the second law of thermodynamics, which is, that systems tend to maximize entropy, you come to a pretty interesting conclusion that eventually the universe will be a pretty boring place and end with, more of a whimper than a bang. And because of the relationship between space, time, the universe's expansion, and the energy density of everything in the universe, this could cause, it will cause the expansion rate to grow over time, right? And basically without any end in sight. And so at some point, the expansion rate can be as large as it was during the stage of cosmic inflation that preceded the Big Bang, right? And as long as the energy in space itself then decays into particle and antiparticles, we could trigger another hot Big Bang, leading to like a rebirth.
Big crunch and big bounce. This is the most uplifting scenario. If there is less dark energy than we think, or it decreases over time, gravity will be the dominating force in the universe one day. In a few trillion years, the rate of expansion of the universe will slow down and stop. After that, it reverses. Galaxies will race at each other, merging as the universe becomes smaller and smaller. Since a smaller universe also means a hotter universe, temperatures rise everywhere all at once. 100,000 years before the Big Crunch, background radiation would be hotter than the surfaces of most stars, which means that they would be cooked from the outside. Minutes before the Big Crunch happens, atom cores are ripped apart before supermassive black holes devour everything. Finally, all black holes would merge into a supermassive mega black hole that contains the entire mass of the universe, and in the last moment before the Big Crunch, it would devour the universe, including itself. The Big Bounce theory states that this has happened a lot of times and that the universe goes through an infinite cycle of expansion and contraction. Well, wouldn't that be nice? So what will actually happen to the universe in the end? At the moment, heat death seems the most likely, but we at Kurzgesagt hope that this dead forever stuff is wrong and the universe will start over and over again. We don't know for sure either way, so let's just assume the most uplifting theory is true.
Well played. So if you look at the equations governing the expansion of the universe, right, you find something pretty interesting. They don't actually give you a value for the expansion rate. They actually give you a value for the expansion rate squared. Now, you might not see the big difference initially, right? But if I told you that the expansion rate squared was equal to 4, well, you would just take the square root and tell me the expansion rate was 2. And then I'd ask you if you were sure. And then you would say to yourself, is he trying to trick me? But the point isn't to trick you, right? The square root of 4 could be 2, but it could also be minus 2. And so when we solve these equations for the expansion rate, we could wind up, with an expanding universe, but we could also wind up with a negatively expanding universe, which corresponds to this, contracting universe. Full cyclic cosmology, which was put forward by like Roger Penrose and some others, right? The universe iterates through like infinite cycles with the future time like infinity, which is the latest end of any possible time scale evaluated for any point, right? Basically, in space, each previous iteration is identified by the Big Bang singularity of the next. So importantly, supermassive black holes, right, in a universe's remote future, which would each have swallowed its surrounding galaxy cluster before, eventually evaporating entirely into Hawking radiation after perhaps 10 to the 106 years, right, a very long time. Then, by something he calls conformal squashing, all of this radiated energy moves into the next eon, the next universe, I guess, as a single Hawking point, right? And these photons, scatter into an expanding region again, right, and don't become free until about 380,000 years after the Big Bang, the CMB, and yeah, the cycle repeats. And he claims that this region of photons that have been scattered, we might actually be able to see this in the CMB, and use that as some kind of evidence for this conformal cyclic cosmology. Biggest predictive difference is that the CCC pretty much requires that an imprint of the universe before the Big Bang, right, would show itself in both the universe's large-scale structure and in the CMB, right? Inflation, on the other hand, basically demands that anywhere where inflation ends and a hot Big Bang arises must be causally disconnected and cannot interact with any prior or future such region. So basically, our universe exists with properties that are independent of any other. And the observations, right, there's been plenty, and there's some recent ones from Planck. As far as we can tell, there are no bruises on our universe, no repeating patterns, no concentric circles of irregular fluctuations, no Hawking points, okay? When one analyzes the data properly, it's pretty clear, and overwhelmingly so, that inflation is consistent with the data, and that the CCC is pretty clearly not. The universe really is on track as far as we can tell, to run out of ways to generate energy. Most of the stars that ever will form have already formed. Most of the energy that will be extracted from matter in all its forms has already been extracted. Most of the structures that will form have already finished forming. Most of the chances for life that the universe could have already passed us by, at least as life as we know it. And so by every measure, the universe's glory days seem to be over. But look, there's still a lot that's going to happen, and some really crazy stuff far into the future. And this all hinges on our current understanding, which you can bet is probably not correct. And so who knows what's going to happen. Don't take it too seriously. I mean, take it seriously, but at the same time, don't be absolutely convinced this is going to happen. There are other possibilities, my friends, but that'll do for now. So I hope you enjoyed the video. Make sure you subscribe. I'll catch you next time.